Okay, so this video is going to take you through three different acid-base theories: the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. Now, you may have actually had a bit of this before, particularly the Arrhenius and Bronsted-Lowry theory. So if that's the case, you can, and you feel like it, you could probably just skip ahead to the Lewis theory, or just watch the entire video. I don't think it's that long. So why don't we get stuck into this? The Arrhenius theory, then, a pretty straightforward theory. The acid defined as a substance that produces hydrogen ions, H+. A base, then, on the other hand, is a substance that produces hydroxide ions. So, for example, hydrochloric acid, obviously an acid because of its name, but here's what it would look like as a dissociation of that acid. And so there's the presence of that hydrogen that Arrhenius was speaking of as required to show that it's an acid. So a base, on the other hand, sodium hydroxide, dissociates sodium ions plus the hydroxide ion. So by definition, a base produces hydrogen ion, an acid produces hydroxide ion. So that was one of the first formalized acid-base theories. There are a couple limitations, however, and so the first limitation, she was trying to explain the neutralization of hydrochloric acid by ammonia. So this reaction actually produces ammonium chloride, aqueous, in solution. And so how does that come about? How does this fit into the Arrhenius theory? Because there's there's potentially hydrogen. There's is with the HCl, the hydrochloric acid, but where's the hydroxide ion coming from? And it was rationalized that actually the ammonia reacts with water, and in that process produces hydroxide ion, and that hydroxide ion combines with the hydrogen ion of the HCl, and that's the production of water. And you also still get ammonium chloride produced. So it was argued that because something reacts with hydroxide ion, it kind of fit into the Arrhenius theory. But then this then they had to explain but the next thing was to try to explain this one. And so if we look at this reaction, we also get ammonium chloride, and that happens to be a solid. And there's no way to explain that, because since the HCl and the ammonia are both in the gas phase, there is no solution. So if there's no solution, there's no reaction with water to produce hydroxide ion that allows for the neutralization process. So that was one of the shortcomings, was this seeming anomaly in the behavior of ammonia and other things like ammonia that didn't contain hydroxide. So the explanation of bases was a little tricky. And the other one was, the other issue was this notion that they couldn't isolate or really see unhydrated protons, that is H+, in solution. On the other hand, they did have the evidence for hydrated protons, and that should kind of make sense. Here's water, and here's a proton. A proton is a very reactive species. It is going to combine with the water, and in fact it does. And if that is the proton that was added there, you've seen this as a coordinate covalent bond, or a dative bond. We've seen that before. And so this is much more likely to be the case. You get this species formed, the hydronium ion. And so, again, the Arrhenius theory didn't really account for the presence of hydronium ions. So a new theory had to be developed. And so that was the Bronsted-Lowry theory. And so this came about the same time. Two chemists put together this notion. They happened to be named Bronsted and Lowry, hence the Bronsted-Lowry theory. And so their definition is a little different. An acid, defined as a substance that donates or loses a proton, an H+. A base, on the other hand, is a proton acceptor, or it gains a proton, and it gains that proton from the acid. So this definition is not limited to aqueous solutions and explains the basic nature of substances that don't contain hydroxide. So this theory was basically an addition to the Arrhenius theory. So it didn't supplant the Arrhenius theory, but it added to it, and added to it in a way that helped explain some of the properties that were unexplainable by Arrhenius. So we often look at this first as a generic reaction, so HA being my acid, so this H is this ionizable proton, the H that we're going to lose. So the acid is a proton donor. It loses a proton. When it loses a proton, it becomes A-, and a base, in this case water, is acting as a proton acceptor, and there we go, we get that hydronium ion. And so these are both aqueous. So that is a generic reaction. How about a couple of others? So we can explain hydrochloric acid in this way quite easily. Obviously, the acid is the proton donor. So there's what's left after the acid loses a proton. Again, plus water, plus hydronium ion. So water accepts the proton. Now in this case, our ammonia is acting as the base, and so it is the proton acceptor. It means water is acting as our acid. So it's the proton donor. So what do we get? We get ammonia, NH4. The base accepts a proton lost by water, and water then becomes the hydroxide ion. And so there are a few examples that nicely show an acid acting as a proton donor, a base acting as a proton acceptor. Just go through that one more time. This is the familiar acetic acid, so it's going to be the proton donor. And so it donates its proton and is left with this anion. And water is the proton acceptor. But I can reverse this reaction, and I've reversed it here. Now what happens in this case? Well, if you look at this acetate ion, the anion produced in the above reaction, it's now negatively charged. It does have more hydrogen it can donate, but it's much more likely to gain a proton. In that case, it's going to act as a base. If it acts as a base, that means the hydronium ion is going to act as an acid, and that should seem logical to you. It has an extra H+ attached to a water molecule. I mean, while it's stable, it's probably not the most stable configuration for water. And so if it does that, if the acetate ion acts as a base, it gains a proton, and we get our water back. The hydronium ion donates water back. So you can see this reaction can be written in one of two ways, and written in either way, you have an acid or a base. So this gives us this notion that is very central to the Bronsted-Lowry theory: conjugate base pairs, acid-base pairs. So what you have is an acid reacts with a base. When that acid behaves as an acid, it becomes or turns into a conjugate base, and the base on the other hand turns into a conjugate acid. And so that's quite evident from that last reaction we just looked at. There's my acetic acid, the acid. It turns into a conjugate base. So there's the conjugate base of that acid. And this base, water, turns into a conjugate acid, which basically means that if conditions arise that are favorable, the reversible reaction can be driven, and it's still an acid-base reaction. So that's why we write it with equilibrium arrows. This is now an equilibrium situation. Let's look at this one now with ammonia. So ammonia and water are going to react, and one of them is going to be acid, one of them is going to be a base. And I look over here and I see the hydroxide ion. So that means the ammonia must be acting as the base. And if ammonia acts as a base, its conjugate acid is what it becomes after it gains that proton. And so there's your conjugate acid. That means water must have been acting as an acid in this case. And when water acts as an acid, it donates a proton. And so there's the conjugate base, what it becomes after it donates that proton, after it loses a proton. So base, acid, conjugate base. base conjugate acid pair, acid conjugate base pair. You can look at it this way. Bronsted-Lowry base gains a proton, it becomes a conjugate acid. So ammonia as a base becomes a conjugate acid, NH4 plus, an extra H plus. On the other hand, a Bronsted-Lowry acid loses a proton and becomes a conjugate base. So there's water, one less proton, take away a proton from water, you get the hydroxide ion. So conjugate acid-base pair is very central to the Bronsted-Lowry theory. Next acid-base theory then is known as Lewis theory, and this is brought out around the same time as the Bronsted-Lowry theory, but it's looking at it from quite a different point of view. And again, simply stated, a Lewis acid is an electron pair acceptor. So in this case, what we're looking at is movement of electrons or transfer of electrons. Well, not transfer really, because they're forming covalent bonds. The Lewis base then is an electron pair donor. And so we can look at that in terms of Bronsted-Lowry and Lewis theory. So remember, we're not changing what a base is, we're just changing how it behaves. So the hydroxide ion as a Bronsted-Lowry base, or sorry, water as a Bronsted-Lowry base would be a proton acceptor, and so it has this lone pair here that allows it to bond to another hydrogen. That's what it does to form the hydronium ion, so it can accept that H plus because of the lone pairs. Well, in Lewis theory, this is a Lewis base because it has those lone pairs to act as an electron pair donor. So one of these lone pairs could act as a donor. And if it donates a pair of electrons for the formation of a bond, then it's by definition a Lewis base. So ammonia, again, a Lewis or a Bronsted-Lowry base because it can accept an H plus due to that that lone pair. So again, a Lewis base because of that lone pair. And there's water again. I'm not sure why water's there again. I think it was meant to be hydroxide ion. Let me just erase one of these. Okay, so hydroxide ion again acting as a Lewis base, once again because of the presence of lone pairs. So it's lone pairs that make them Lewis bases. So again, the hydroxide ion, if it gains a proton as it would as a Bronsted-Lowry base, it is acting as a base. If it donates an electron pair as it would as a Lewis base, it becomes water. So we aren't changing these as bases, we're changing the way we look at them as bases. So as Lewis bases, they are electron paired donors. Another example, so you've seen this before in in structure and properties, ammonia bonding to a boron complex. Remember, boron trifluoride is electron deficient, and so in this case we have a lone pair that is going to make NH3 ammonia a Lewis base. And because it's a Lewis base, lone pair donor, that must make the BF3 the Lewis acid. And what happens? Well, you form that coordinate covalent bond. So again, there's that dative or coordinate covalent bond formed. And so the Lewis base donates the electron pairs of the bond, and the Lewis acid accepts the lone pairs. And one last example, again, this is the one that allows you to look at the neutralization of ammonia with hydrochloric acid in terms of Lewis acids and bases. So again, quite obviously the ammonia is going to be the Lewis base, but how does HCl act as a Lewis acid? Well, one thing to realize is that polarity of hydrochloric acid. Remember, hydrochloric acid is quite polar, HCl is quite polar, and so delta positive, delta negative. And then we can look at this in terms of movement of electrons. The curly arrows, we saw these in organic chemistry. So as a Lewis base, there's the pair of electrons that are going to be donated. They're going to be donated to the delta positive component, the hydrogen, and those, once it gains those, all those electrons end up moving towards the chloride. And so what you end up with is the ammonia ion and the chloride ion. So HCl is in fact the Lewis acid. It accepts an electron pair, but it also splits in the process. And so that's how you end up with that neutralization. So you get ammonia plus the chloride ion. And so so the three different acid-base theories, the Arrhenius theory, the Bronsted-Lowry theory, including conjugate base pairs, and the Lewis theory, where the bases and acids behave as electron donors and electron acceptors. So those are three theories you should endeavor to have a grip on, come to terms with. And that concludes this video.